Uh, Good afternoon, and happy to be back at this StatFiz meeting. Uh, Today I'll be talking about some work on creep response in amorphous solids that we have been doing. And the main results of this work is actually done by the chair of the session, Momita. And it builds on previous work by Shumon, who is in the audience, and my collaborator, Kristen Martins from Grenoble. So creep is very common in materials that we use, or even in the world around us. So, for example, here, this is a cartoon of creep happening in the mountains, where because of the gravity, the soils below the surface starts moving, and you can have weird things happening, like buildings cracking and roads cracking and so on. So we would like to understand how creeps occur and also how to prevent creep and so on. So our focus is on amorphous materials or disordered solids, and these are in different shapes and forms, starting from metallic and silicate glasses, which are very atomistic glasses, and to granular solids and so on, and it spans a huge size scale. So because it spans a huge size scale, there are thermal systems and athermal systems. So thermal would be these kind of materials like metallic glasses, colloidal glasses, and so on, and granular materials would be the athermal ones and so on. So irrespective of whether they're thermal or athermal, the characteristic feature is that they have an yield stress. So for example, if I'm applying a load, I have to increase the load beyond a threshold in order to make it flow or deform deform irreversibly and so on. So what we would like to do in this, or what we are doing at this moment, is applying a stress on these amorphous materials and asking how they are responding to this stress and so on. So this is very commonly done in the experimental lab. So this is a thermal system. So this is a granular suspension. So they are applying different stresses. So if you apply a large enough stress, then the system flows at a finite shear rate. And if the stress goes below a certain threshold, then it gets arrested and so on. So for the thermal systems, it's either flowing or it's arrested if it's above and below some stress threshold. On the other hand, if you're in thermal systems, it flows if it's above some threshold. And if you're below that threshold, it's still flowing. It doesn't have a finite shear rate, but it has some kind of a power law behavior with time for the strain. And this has different exponents, and people have been reporting different exponents and so on. And this work claimed that there is eventually asymptotically a logarithmic growth of the strain at long times and so on. So obviously, experiments can't access microscopic information, which we can do via microscopic models, and that's what we are working on. So just to set the sort of the framework. So if you have a material at rest and you're applying a stress, then initially there is some elastic deformation. Then above some stress threshold, it starts to fail. If you have a solid like this, it will rupture. If you have a fluid like toothpaste or something, it will go into steady flow and so on. So you can take these steady state numbers and stick it over here. So you have stress versus shear rate, and you have a flow curve. And then you can ask the question that if I'm starting at a flowing state and I decrease the amount of stress, at what value of stress will the system stop flowing? And this will give me my dynamical threshold. On the other hand, if you start from a state of rest and you impose the stress, then there's a certain value of stress at which it starts yielding, and this is the static threshold, and this depends upon history. So you can think of it like this, that if you are running down the mountain, if you will stop at the first minima that you find in the case of the dynamic threshold, but if you're starting from the valley, then depending upon the depth of the valley, you will get to start moving or traversing the landscape and so on, and that would be the static threshold. And this people have found in numerical simulations that the static threshold indeed depends upon the history and so on. So the model system that we are studying is a well-known by Lennard-Jones mixture, and you have about 100,000 particles. And all the features are known about this model system, and people have been using it for study different mechanical properties and so on. So what we do is basically take this model system, thermalize at finite temperatures, and then quench. So this is a very complex landscape, typically of a glass forming system, and you get stuck at different local minima depending upon where you start quenching from, and you can generate a whole family or bunch of inherent structures or different local minima depending upon your preparation history and so on. So is this time remaining? Okay. So if you have an athermal system, So this is some previous work that we had done. I have to go fast. So if you are above some stress, then you start flowing, and below some stress, you get arrested. And so this numbers that you get for the stress threshold around 0.8 is much larger than your dynamical threshold, which is around 0.511 and so on. And there what we had done is basically we could look at two stresses which are very close by and start from the same initial state. And suppose you have a stress difference of about 1.006 in this resolution, then you could see that in one case it goes into arrest, in the other case it goes into flow. And when it goes into flow, this is the sequence of states that we go through it. So till a long time, all the sequence of states are almost the same, and suddenly there is this bifurcation that is happening. In one case it goes into flow, and the other case it gets arrested. And we could identify what are the structural signatures which leads to arrest and so on. So what we do next is we couple it to some thermal bath, and our temperatures are sufficiently low that you only get some thermal vibrations that are happening. So these are some movies. These are not playing. So the movies are not playing, sorry. And then, so if you then couple this, if you take these thermalized states and then start imposing some stress on it, of course, at large stresses, it starts flowing. But if you decrease the stress, then you start seeing this sort of creep motion where the system is not arrested at long times, but there is some finite deformation that is happening and so on. So what we have done is basically we have identified as a function of temperature, what are the static thresholds and what are the dynamic thresholds for this system. And what we see is that, of course, under athermal conditions, this gap is quite large. And if you start with this particular history and then thermalize the system, then this gap starts decreasing as you go to larger and larger temperatures. And this is reasonable to understand because as you thermalize more and more, you are able to hop across barriers, and therefore you're able to go closer to the dynamical threshold and so on. So then you can ask also what would be the exponents that are sitting over here, the creep exponents and so on. And so for the thermal case, we get an exponent of about 1.65. And for the thermal case, we get an exponent of, or we get this 1 by T kind of behavior, which is very similar to what was experimentally reported and also matches with some recent schematic models and so on. And hopefully the movies play. So finally, we would like to look at the microscopic picture, what is happening at the microscopic scale. It's playing. So this is the case where the system gets arrested, and you see some patterns, some plastic events that are happening, and eventually the system will go into arrest, or nothing as much is happening, and the other case, it should flow. So you almost have the same patterns that are repeating in this case, where it gets arrested at the end, but in this case, it will go into flow. I have one more slide, so I'll finish after that. So and then it flows. And if you increase the thermal scales, this plasticity goes on. So here it's creeping for a long time. So the plasticity proceeds in a similar fashion in both cases. In one case, it goes into flow, and the other case, it doesn't flow, or it doesn't go into the steady state at long times. So again, the patterns are exactly the same, except that in the final, in this case, you have more plasticity that is happening that leads to the flow. And we need to understand this microscopically better. These are some initial results that we have. Okay, so to summarize, we are probing the interplay of mechanical and thermal noise in the context of yielding. And we observe this prolonged creep, and our exponents match with theoretical predictions. And so what we can say at this moment is the fluctuations continuously activates local plasticity, which leads to this creep and so on. Thank you. Yeah, and if you want to see further discussion, you have a poster by Momita tomorrow.
Questions?
Yeah. Stress. Yeah. So, yeah, fine.
Any other question? So if there is no more question, so let us thank the speaker once more.